We have a couple of panel sessions, in fact 3 panel sessions yet to go in the afternoon. I'm Tariq Samad. I'm with the Technological Leadership Institute at the University of Minnesota. For those of you who were in Minneapolis last year, where we held the first Trans-Atlantic Symposium on ICT Technology and Policy, I was the main organizer for that one, along with, of course, Svetlana Klasova and others. And I'm also the co-chair of the IoT CPS expert group in PICASSO, and the chair of the IoT CPS expert group in PICASSO is Sebastian Engel, who will be coming up here after me. But I did have some preliminary comments. So as you know, IoT CPS is one of the expert groups, one of the 3 technical teams, in addition to a policy team in PICASSO. And so we have this panel session addressing and discussing some of the outcomes of that theme. And after some discussion, you know, the IoT CPS is, of course, a very broad space, and we'll be talking about some of the breadth. But we also thought it would be interesting to focus a little bit on one particularly important domain from a smart society, smart community perspective, and that theme is smart energy. So I thought I'd just throw out a few questions. Some of these questions will be addressed by the panel in their remarks, and then I have another slide with some questions that I think you should keep in mind as you listen to the presentations, or as you just think in your minds about your own thoughts on some of these topics we're addressing. And really, I think the value of this session is going to be not just in the presentations, but in the discussion that we'll have as well. So as I said, CPS IoT is a broad theme. So what are some of the key aspects of this? And in particular, we started hearing about this, in fact, from the keynotes this morning, that these disciplinary connections is something that are getting to be more and more important to make. And CPS IoT is a very interdisciplinary field in itself, and it connects with many other disciplines and many other domains, many other application domains in particular. So what are some of those connections that we want to highlight? CPS IoT, in order to be scalable, in order to have the impact that it could have, needs platforms, needs frameworks, needs ecosystems. And you'll see some discussion of such frameworks and ecosystems in the presentations to come. Our energy system, our energy infrastructure, of course, needs to be transformed if you're going to address issues of energy security or energy and the environment or energy economics. And how is that transformation going to be enabled by CPS and IoT? I think we're all convinced that big data, pervasive sensors, connectivity everywhere, consumer engagement, all of these things, which are all things that the CPS IoT world brings, are going to be essential. But what are some specific ideas that could make that happen? And you'll see that addressed too. Yeah. In the international space, what international collaborations are being pursued, have been pursued? What are some of the lessons learned? What are some best practices? Within the PICASSO project, within this expert group on CPS IoT, there's been a fairly substantial effort in assessing, doing a survey on what's out there, what has been done, what are the challenges, what are the obstacles to better collaboration, but also what are some of the success stories too. And so you'll hear about those as well. Yeah. And some other broader questions. We often talk about the differences between bottom-up and top-down collaboration. So bottom-up means researchers get together, they have common interests, they figure out how to collaborate, and they make things happen. And we see a lot of that happening. And the top-down perspective is something that's more policy-driven. Maybe there are collaborations at the governmental level in joint programs. And in Dawn Tilbury's keynote this morning, she talked about some such programs in NSF. So what are the pros and cons of these, and what are the opportunities and challenges associated with these? And certainly they apply in IoT CPS, but they apply more broadly as well. So keep that in mind as you sort of think about what you're hearing in this panel. Smart energy, of course, is not just a national priority or a regional priority. It's an international priority. And what coordination is happening in that space and what coordination needs to happen. To what extent should things be just go in siloed ways, and what benefits could there be to collaborate more deeply in that space. Industry engagement differs quite a bit, I feel, between the EU and the US in some of the programs. So NSF, for example, primarily, almost entirely just funds academia, whereas programs like PICASSO and other European Commission initiatives allow industry to participate. So industry participation, at least within these two sort of frameworks, tends to be quite different, and that makes leads to some interesting dynamics as well. Specifically in the CPS IoT space, there's this notion of autonomy and autonomous CPS. And in fact, tomorrow in the breakout session on CPS IoT, we will be focusing on the autonomy question too. But there's this interesting contrast and conflict perhaps between autonomous systems and human-in-the-loop systems. Which is better? In which conditions is which is better? Which ones should be given more priority? And so I have phrased it as a question: autonomy or human-in-the-loop systems. I think the answer to that obviously is yes, but exactly what does that mean and which conditions? And let's not just think about differences amongst different regions or nations or whatever. Let's also think about all the commonalities that exist. Commonalities certainly in terms of priorities and interests, but also in terms of collaboration mechanisms too. And thinking about that, certainly to me, PICASSO has been an outstanding initiative that has helped bind things together between some groups in the EU and the US. So a question that's, I think, top of many of our minds who've been working in PICASSO the last few years is how do we continue this path forward? Okay. So some other thoughts to keep in mind, and maybe you have some answers there too. So with that, let me just introduce the panelists, and then we'll get going with their presentations. So we'll start by Professor Sebastian Engel. Professor Engel is with the Technical University of Dortmund in Germany. He's also, as I said, the chair of the PICASSO Expert Group on IoT, CPS. He's been involved in several European Commission projects in the CPS space, in systems of system space, in process management as well. Mr. Jose Gonzalez is the International Coordination Manager with FIWARE and also associated with Interinov. So he'll be talking about an ecosystem for smart applications. Then we have Dr. Anuradha Anaswamy from MIT, who will be presenting some of the work that she's doing, coming up with a new framework, a dynamic framework for smart energy systems. And we'll conclude with Dr. Kishan Baheti from the National Science Foundation, who will overview some of NSF's programs in distributed energy management, and he'll refer to some international collaborations in that context as well. We'll see if there's time for a quick question or two at the end of every presentation, but really I would prefer to leave most of the questions and perhaps all of the questions for the discussion after the presentations. So thank you very much for your attention so far, and I'll hand the podium over to Sebastian.
Yes, thank you very much, Tariq, for the great introduction. Yes, things will get a bit more technical now in this session. I don't know whether I should apologize or not. It's like when you teach a course after the first lecture, usually it's very nice and everybody understands it, and then things get serious. Okay, so I want to introduce a little bit of the work of the expert group in PICASSO and have a bird's eye view on the domain of IoT and CPS, and also on possible collaboration mechanisms. And then I think we get more into technical things, and then we get back to funding issues with the presentation by NSF. Okay, so what we focused on is the convergence of IoT and CPS. So when you look at especially the European work in IoT, it is very much about platforms, connectivities, middleware, and we are now at a state where even if there are technical issues still open, one could collect and one can collect and one does collect a lot of data in real time. But then the question is what to do with all this data. There are obvious and things like that were also discussed in the previous panel already, related, for example, to consumer goods, to personal behaviors, etc. But here we are focusing on technical systems, and then we talk about real-time usage of data to manage complex systems, to go from sensing to actuation to closing the loop. And so here in the expert group, we saw IoT as an enabling technology for cyber-physical systems, and especially for large-scale cyber-physical systems. You know that the concept of cyber-physical systems is relatively broad. I mean, if you take your mobile phone or your camera, it's a cyber-physical system. It's a mechanical, optical, whatever system, and it's controlled by a computer. But let's say if you look at large-scale cyber-physical systems, then you get different, like energy systems, road traffic, production systems, you get different properties that one has to deal with. And in another project, we coined the term cyber-physical systems of systems for that. And I will spend a few minutes to talk about these. An example, which I cannot explain in detail due to lack of time, is the vision from a few years ago by Siemens on about how to operate the power system of the future. And what you should keep in mind is that all these different factories here, photovoltaic energy producers, consumers, they all have a so-called agent that decentrally manages its own system. But then, of course, somehow this grid has to be kept in balance. Which can, of course, be done somehow automatically, but you know that also in an electrical grid, there are economic mechanisms that are used to keep production and consumption in balance, which you can take as an incarnation of this balance master here. Okay, so cyber-physical systems of systems are systems which are cyber-physical in the sense that they have a lot of computing and communication, but also a physical aspect, and then they are large. Okay, so they consist of many different units, agents, and they interact, and this interaction makes it even more complicated to run them optimally. I would just like to touch on two properties of these CPSOS. So one is that the control and management is not done completely centralized or top-down, but there is autonomy on the lower layers. And this partial autonomy on the one hand side makes the system robust. Okay, so a system that is completely centrally controlled will probably never work. But on the other hand, you have a problem that the subsystems have their own goals. They interact, they consume resources. They may do things which are not in the best interest of the overall system. And how to bring that all together is an interesting research topic. And the second thing is that a large cyber-physical system or cyber-physical system of systems evolves over time. It evolves geographically. It evolves in terms of the elements which are part of it. If you think, for example, of air traffic control, if you think of traffic, of railroad systems. So components may come and go. The system structures change. You have different demands, you have different resources, you have to react to faults, to breakdowns. Think just of a railroad system as okay, in the US you don't have these big railroad systems on which many people rely, but in Germany or the Netherlands it's a permanent topic that people tell stories about how they got stuck on some train station because their connection failed. And these systems operate and are continuously improved and modified over long periods of time. That holds for the electricity grid, it holds for all transportation systems. So engineering of such systems is not something that you do on a green field, but it is re-engineering and it takes place at runtime, and this puts challenges on these systems engineering methods. Okay, that's a quick overview of the members of the expert group. So you see that we have a representation from academia, but especially also from various companies, both in the US and in Europe. And I would like to, sorry for being a bit fast, but otherwise we will have no time for discussion in the end. I would just like to give you the highlights on the so-called opportunity report that this expert group, together with the other expert groups in PICASSO, produced. And the main author is Christian Sonntag, who was a senior scientist in my group. He has now left to industry, which is the reason why he's no longer with us. He cannot be with us today. So we did a lot of analysis, data collection, interviews, analysis of strategic documents in order to find out what are the differences and what are the common topics in research and innovation in cyber-physical systems and IoT in the US and in the European Union. Also, this is too much text to be read in the time given. So what you can see here are the high priority and the lower priority research topics together with the number of projects funded in these areas, both in the EU and in the US. And you see that the correspondences are quite strong, okay? So the view of the world, the view of the needs, of the future needs in research and innovation are very similar. What you also may see if you have good eyes is that sometimes the number of funded projects does not really correspond to the question whether it has high priority and lower priority. So that also has something to do with the evolution of funding programs. So the funded programs are always a reflection of the work in the past, of course. So that was for CPS, and it's very similar for IoT, that the topics are quite similar, that are of prime interest both in the EU and in the US. And based on this, we synthesized a number of core topics which we think provide the best opportunity, which are the most interesting, challenging ones at the moment, and which also provide a potential for joint R&D. Okay, one of them is closing the loop in Internet of Things enabled cyber-physical systems. So if you have really a lot of data that comes from different sensors, if you have these different elements of a system that somehow act control on the system, how can you actually make sure that the overall system, like an electric grid, is orchestrated in the best possible way? Then you have the issue of integration, interoperability, flexibility, and reconfiguration. How can you integrate new sensors, new elements, new computing elements into the overall system? How can one realize plug and play of components? And I think that's a prime topic in the Internet of Things domain. Then for these large systems, obviously model-based systems engineering is a big topic. It has been a buzzword in systems engineering probably almost since the term systems engineering exists. And it comes with a lot of challenges. And the bigger, the more heterogeneous systems become, the more challenges you have, of course, to engineer them, to model them, and also simulation becomes a big problem or a big topic, a big challenge if you have systems that have very different timescales, very different elements. So what are the right formalisms and how to put them together if you want to model and simulate the system? We have already discussed in the morning a lot of, not a lot, but a little bit on cybersecurity with a focus on privacy. But also for technical systems, I would not follow what was said in the panel in this morning that somehow security is a subtopic of privacy. I would see it the other way around. I mean, if you see it from an industrial application, then security is the prime concern. Whether somebody can tap into some streams of meaningless data for the party that is able to tap into it may not be very good. But if somebody is able to fuzz around with your chemical plant where you have highly poisonous substances and you manage to blow up some system and you spread this into the environment or over people, then it's a much more serious concern. And then Tariq mentioned that already. It also was in the presentation by Dawn Tilbury in the morning, autonomy and humans in the loop. I think that's a big technical topic that comes up in many areas. We have a separate session on that. And that's also why we focus this session on energy systems, to have a bit of a broader perspective. And as Tariq also mentioned, the role of humans in the loop, collaborative decision-making, information presentation. How do you enable humans to interact with really complex technical systems? And finally, also this is something that has been discussed before already. How can one use with all the data? How can one make use of all the data that is collected to do real-time data analytics in technical systems, adapt the behavior to the situation, recognize critical situations or different patterns in large systems? And from the point of view of the expert group, we think that this topic of autonomy and humans in the loop is probably the most promising one also for transatlantic collaboration, because it poses a lot of fundamental questions. For example, like how do people really interact with complex technical systems? How does that go on in the brain? What is the perception that the operators or the users of a car have of that technical system. Okay. It has also been mentioned in the morning that, let's say, if you balance between competition and collaboration, then between the EU and the US, the pendulum has swung in the direction of competition. And to be fair, that's not only a phenomenon on the US side, but this has at least caused, maybe it was there before, also a reaction on the European side to be more thinking about increasing our competitiveness against others and not together with others. Okay, so that limits, in a very economically interesting domain like cyber-physical systems and Internet of Things, that limits the possibility of doing joint R&D projects to some extent. And therefore we think that the immediate steps towards more collaboration should be more on the scientific, in the European slang, low TRL, technological readiness levels areas, so to do road mapping and benefit assessment via joint workshops, and NSF has already sponsored such workshops, not so much with the EU, but with member states of the EU. So to come up with road mapping, to refine that, to facilitate collaboration initiatives, to have maybe somebody who's able to do some partnering, and to do lightweight joint research and innovation, to use fellowships and exchange funding programs to launch possibly synchronized initiatives that support each other on both sides of the Atlantic without money crossing the Atlantic, and without, that was also discussed, and Dawn Tilbury said the same, nobody at the moment is interested in having very complicated mechanisms and joint panels that evaluate proposals, etc. So one must find solutions which are easy to handle and which enable both sides to, let's say, preserve their strengths, their identities, their specific ways of running projects, and to synchronize between them to get the optimal benefit for everybody involved. Yeah, that's it. Thank you very much for your attention. And
thank you, Sebastian. So, when in the early days of the PICASSO project, we had quite a bit of discussion about how we are putting together these two very broad areas, IoT and CPS, and what does that mean? There's such a broad space now. Can we really make meaningful progress in something so broad? And so what we ended up doing was really focusing on IoT, CPS in the sense of applications to real-time systems, to cases where the physical world has some significant play there. And so that ended up being a major theme, which I think has driven a lot of the work, and certainly smart energy is a prime example of that. So next we'll turn to hearing more on the IoT side and hearing about FIWARE, which is one of these ecosystems that is emerging for IoT.
Thank you, Tariq. Good afternoon, everyone. My name is Jose Gonzalez, and you will see that the presentation is called FIWARE Introduction, and you will see an introduction of what. So this is what we will see today. I mean, today I only have like 10 minutes, but it could be like 2 days, because like a month ago we had like 2-day summit with more than 400 participants. So FIWARE, you will see that it's, even though you may not what it is, but it has a lot of impact, at least in Europe. And for example, guys like me are trying to make it more global. So you will see a little bit more what it's about. Tariq was mentioning before about bottom-up or top-down. Actually, FIWARE, it's a success story of top-down approach from the European Commission. And we will see later why it's this because, basically. So this is not going to be technical at all. So you can you can take it easy. And actually, we will have a couple of minutes video, because probably the video will explain it a little bit better than me.
We are approaching a new digital revolution. More than half of the world's population has an internet connection, resulting in continuous streams of data generated by the technologies we use in our day-to-day lives. The Internet of Things is impacting virtually all stages of economy and social life, representing a profound change in how humans interact with machines, information, and even each other. The increasing maturity of big data, cloud solutions, and new internet-connected devices have created an exciting and valuable opportunity to build the next generation of data-driven smart solutions. Information coming from multiple sources must be accessible in real time, creating a digital continuum. Breaking down boundaries between domains will enable the exchange of relevant data across multiple applications, avoiding the current silos of information. FIWARE is driving the standards to make all this happen, unleashing the potential of real-time open data at a large scale. It simplifies IoT, allowing developers to merge IoT data with data from other relevant sources and get access to it using well-defined RESTful APIs, reducing both the time and cost of development for IoT-enabled smart solutions. Thanks to harmonized data models and APIs, developers are able to create applications that are truly interoperable. Real-time data exported in a city can be combined with data from vehicles acting as mobile sensors to enable new services and improve processes like predictive maintenance of fleets and roads. Systems associated to milling and coordinate measuring machines in a factory can exchange data in a trustworthy manner for a better performance. FIWARE ensures the sovereignty on data, allowing the appropriate levels of access to data to be defined, for instance, for potential monetization. Data from vehicles can be published on a data marketplace supported by the city, so it can be monetized when used by third-party developers. FIWARE Context Information Management is the basis for the new data economy and the creation of innovative business models in multi-sided markets. Join us to ensure that standards are driven by the needs of all society and to ensure that FIWARE will stay free for all, forever. We are approaching a new digital revolution.
Well, so, I mean, that's what FIWARE as a platform is, but I don't like it, to be honest. I mean, the concept of FIWARE as a platform is actually it's much more behind. It's one ecosystem. It's part of FIWARE itself. It's not a vendor. It's not a service provider. It's actually an ecosystem of a lot of people behind it. We're talking about here about industry. We're talking about here about universities, research centers. We are talking about small and medium enterprises. That's actually the good side of FIWARE. It's about the ecosystem idea that it's behind. A lot of open ecosystem that it's working with each other to trying to come up with better solutions. So I like this slide because it reflects what FIWARE is. FIWARE started in 2010 but by a huge program driven by the European Commission. This is why I was saying that it's top-down, basically. The European Commission decided to start it, and it's $500 million of investment. So basically, throughout 8 years, we have been, working on the platform. That's true, but I mean, we have created an ecosystem that it's behind, and that's actually what I like the most. I mean, the concept, the idea of the ecosystem, because thanks to this investment, actually, 1,000 plus business ideas were supported. And actually, this is how we can really start creating the ecosystem behind. I mean, why do we need a platform if it's not working, if it's not used by anyone? So actually, this is why it's important, the concept of the ecosystem that it's behind. The customers, the users of the platform are the most important thing. Okay, so thanks to that, for example, more than $20 million has been raised by companies that are using the platform, a platform that it's open source, okay? It's open source, and the most important thing, it really focuses on the one standard interface. But one standard interface, so let's go through the principle. The principle behind it's basically in the city or smart city, what is smart, basically? We can have, for example, we have multiple sources of information. For example, if we want to know what is the temperature in a given location, we can have a sensor deployed in the street. We can have like a user with a smartphone, or we even have the public transportation system that collecting data. So at the end of the day, we can see the city or any kind of smart system as a context information pool, okay, a different data. So on the top, we have application and services that are using this data. So what the principle that it's really behind FIWARE is try to come up with a common and standard interface that we call NGSI. So if we can really translate all the data that it's collecting throughout the city or the energy system or whatever you want to use, basically, and put it onto a common interface for the applications, we can actually unleash a huge marketplace that it's about the data economy, okay? So basically what we did, it's like we pick up open source technology, reference one, like for example, OpenStack, Docker, Hadoop. I mean, we didn't really reinvent the wheel, basically. We pick up open source technology and put it a standard interface on top of that. It's like a Lego block. So if we think of a FIWARE service like that, could be, for whatever use, and we replicate it in different things, like you use it in a platform, we can actually have different building blocks to create smart applications. Smart applications to use data in a common way. So basically we have three main things, like it's interoperable because it can work with Amazon Web Services, it can work with IBM Bluemix. The most important thing is to try to work with each other. It's modular, basically you can pick up as many blocks as you want. I mean, since it's open source, it's free, basically you can use whatever you want. And it supports a lot of vertical markets. Today we're talking about energy, but it could be like smart cities, agriculture, could be anything, okay? So yeah, basically with this, the benefits of the approach is basically we create an open innovation ecosystem in which each partner work with each other, in the sense like it's not only me creating a solution, it's actually I'm working with someone else to create a better solution, and I can actually to reuse another solution that has been done already. We try to avoid the vendor lock-in, for example, for smart cities. Instead of like leveraging on this on a given vendor, we can actually create a ecosystem of working with different local players, okay? And actually, we can reduce the cost because we use services that I have already in place, okay? So why it's important that I'm saying this today in a EU-US cooperation? Basically because it's starting in Europe, but actually we are spreading all over the world. For example, we have been working with the US since 2014. Actually, we are partners of NIST in the Smart City initiative that they are leading, and that is called Global City Team Challenge. And it's actually this week there is a conference there. But we have cooperation with Canada, with South America, with Asia. I mean, it's an initiative that it's global at the end of the day because we are setting common principles. And what's behind, actually, there is a platform, but I mean, the most important thing that it's service providers that are behind. I mean, local companies that are actually using the platform to create business and to work with each other. And this is actually why we developed this FIWARE marketplace. And we actually are using this marketplace to create cooperation all over the world, to take these companies that are using FIWARE and, for example, help them, deploy their solutions in Canada or here in the United States, okay? So given that we are running out of time and the panel itself is about energy, I want to give you an example of how the platform is being used in the energy sector, okay? So there is actually a project that it's a couple of million euros that it's called FISMAP. The motivation of the project is basically how to reuse the FIWARE services, the platform itself, for energy-specific uses, okay? Basically, the motivation is like there is an increasing need for flexibility in the sector, okay, especially in the integration of renewable and decentralized energy. So basically, their main goal is to create a smart energy platform, but instead of doing it from scratch, they're using the FIWARE platform. I mean, basically, if there are some building blocks already working with it, why not try to use it, okay? Because the goal is to operate an efficient, automated, and sustainable energy supply for single buildings and municipalities. So basically, they come up with 3 field tests in Sweden, Germany, and Romania, okay? So just an example, basically, I will show the details field in Sweden, for example, where there are a couple of scenarios. One of them is in the smart city of Malmö in Sweden. And the other one is in Living Lab of university and on the university campus, basically. So the approach is the following. They try to connect a number of households with the smart grid platform that it's actually want to work with FIWARE, okay? And they are going to manage various energy sources, including the electric and thermal, basically. They're planning to monitor and analyze the different behavior of these users, of these households, and the final objective is to influence the user behavior towards a lower energy consumption, okay? And also for the test field in Germany, basically they have actually deployed a medium voltage reserve grid, where actually they expect to implement a multi-thermal DC grid, well, several steps, but at the end of the day, what is the goal behind? The goal behind is to bring utility closer to companies. At the end of the day, we have to bring, open up different business opportunities for this data that it's being collected. And not only that, it's like new energy services and business ideas trying to use it through FIWARE. At the end of the day, it's trying to use knowledge that has been already created and put it in open up a market opportunity. Okay, so I mean, this is a couple of examples. There are some of them, but I mean, I thought it was nice to have it in mind. As I said, I mean, a lot of things about FIWARE. So I mean, I'll be here around. So if you have any other questions or more information about what we're doing here in the United States or anywhere else, I mean, I'm happy to answer that.
Thank you very much. So we are now sort of transitioning gradually from discussions of general IoT and CPS and IoT to now more specifically smart energy and the CPS space. And Anuradha Anaswamy is going to talk about some of her work in this area.
Good afternoon, everyone. So the previous talk, as Jose mentioned, was not that technical, so this one will be technical, so there will be a quiz at the end. So this is, I've been working in the area of smart grids for the past 7-8 years or so, and I wanted to share with you sort of some of the highlights of how we see as researchers, as technologists, this field evolve and how it intersects with the overall topic of the symposium. And it's really great to have this opportunity where, you know, typically the talks that I've given are to a bunch of engineers. So it's really nice to have all of you policymakers and economists and administrators and regulators in the room. So because indeed, all of us will have to come together to address these challenges and seize the opportunities. So from a technologist perspective, and again, like Tariq mentioned, my focus will be on a power grid, so electricity. So let's start with that as the final product that we are after. So a smart system, one where you make decisions using information, which is really what we think of and technically refer to as control, we want to make sure that some of the basic operating limits are maintained, that there are limits to how much voltage you can push through, how much power you can push through, and you need to, and since the electricity wars were after Tesla and Edison fought them and Tesla won, it was really AC, so electricity comes to you in the form of AC, so you need to maintain the frequency around a certain value, and you need to make sure that there are no fluctuations. So that's really what needs to be done, and some of these folks have to talk to each other. But what's happening, and so typically, you know, you needed to have markets decide as to how much power, who's going to produce how much power, and then that is sent through transmission, through distribution, and reaches you and me. And these are the guys have to come together, and that's basically what an energy system typically did. But what's changing is basically that world over, there is a push towards basically making the energy sustainable, make it green, so you embrace more and more renewables, so use solar and wind power in order to generate electricity. But there is a significant technological challenge, and that is that here, what you see here is just basically wind production over a one-day period, and all possible power production between 0 and its maximum is possible, given that there is a significant amount of variability in how much wind blows. And the same thing is true for solar energy as well, because the sun can indeed shine or not shine on a given day, a given hour, a given week, anywhere in the world. And so how do you then make sure that this technology is indeed delivered reliably? And so it turns out that these decisions that are made basically span a whole variety of timescales. And so you've got all of the planning that has to take place and the operation. So this is the technology space, and this is the regulatory policy space, if you will. So this is, in some sense, global, and this is, I suppose, local. But still, they all have to come together in order to make these different decisions. But what is really challenging this paradigm is the fact that these renewables that we want to integrate into this technology is something that is spanning, that is sitting right in the middle, and therefore, the way in which you need to make decisions and have a smart energy system is really changing. And so the timescales that you typically have in markets, in the regulatory space, and in what kinds of actors come in and provide what kind of service is really changing. And that's one of the biggest challenges from a technology perspective. And so what used to be these very few agencies and entities and stakeholders have really multiplied enormously. And now we are talking about not only renewables, but then the right power electronics has to sort of pull them together. And there is this notion in which you can incentivize perhaps every one of us to either consume less or more electricity, because that might be then more appropriate and more efficient for the infrastructure, and manage costs better. Then you've got a number of electric vehicles that can serve as storage devices, and the distribution system then will have to pull all of these together. It could be very well that, like what Jose was talking about, the FIWARE is the one that pulls these guys all together, but still we need to make sure that the right information is collected and the right decisions are made using that information. And that really needs to happen in order for a smart energy system to come together. And this is also, I think, great that we have a number of different disciplines, people coming from different, experts coming from different points of view in this room, because it's the policymakers then really do have to worry about the fact that how all of these people are going to come together in order to meet a global outcome while making sure that the local interests are indeed preserved and privacy is preserved too, like the panelists were saying earlier today. So if you were to trace the path of electron, then basically it starts from generation to transmission to distribution to consumers, and the agencies that make these decisions basically are markets and control. So what I want to do is to just give you three highlights, just to give you instances of how these smart energy systems come about and what the challenges are in each of those things. So the first that I'd like to talk about is market structures. I'm glad that there are some economists in the room too, and so hopefully we'll have more discussions afterwards. Because what changes really when you bring in wind and solar into the picture? So I'd like to talk a little bit about that. As you go down closer to the end user, what's also an interesting feature that is happening is that thanks to huge technological advances with smartphones and distributed computation and cloud computing and so on, that the periphery of the grid is becoming more intelligent, which means that the distribution system is becoming highly heterogeneous, and disparate stakeholders have to participate. And again, how do you make sure that indeed they do have a common language to communicate and make the right decisions? So I'd like to say something about this. And the other interesting thing is that this whole notion of cyber-physical system and Internet of Things is actually bringing to the surface other interdependencies that we normally do not think of. And that's the last thing that I want to talk about, which is that as you really increase the green component in the energy production, you really do need to worry about interactions with other infrastructures, like, for instance, natural gas. And so there are some very interesting possibilities that exist in order to really make the overall infrastructure more efficient and more resilient, and by exploiting this interdependence in a beneficial way. So I want to just give you that as a third example. And each one of these things, again, that was mentioned by the plenary speaker, it's not only a challenge, but also an opportunity. And so examine what those might be. So to start off, typically the way economic dispatch works is that there's an independent system operator, and this is a more US-centric deregulated perspective, and there are some variations from place to place, and so you collect all of the bids, and then ISO posts a schedule, and that information is then transmitted to the participants in the market, and they basically generate a certain amount of electricity. But given that you've got the notion of renewables entering the picture, one might really need to utilize real-time information and make decisions quickly and reliably. And that is another an opportunity by essentially you're making the energy system smarter. So one of the things, and again, I mean, like Don only talked about X in the morning, so I'm going to talk about lambda also. So what this is really saying that in addition to communicating the generation information, you need to also communicate what might be the possible price that you pay. So some of these systems become more efficient by bringing in a transactive energy component where the amount of energy that you're either willing to generate or consume is something that is incentivized appropriately. And so having a dynamic market solution like this might give you a better way of integrating these disparate stakeholders. For example, this is a simulation study here. I know there's a lot of information. The main thing I want you to focus on, what you're looking at, this axis is basically a 1 hour period. So every 5 minutes, the market is making a decision. And these are all the participants in the market. And so what you don't have control over is how much wind is blowing, say, for instance. So hour 7, let's say the amount of wind suddenly drops. So all of these other actors that are participating will have to come together, and that is facilitated because the energy system, what we are proposing here as a premise, is smart. And so what this does is basically the amount, not only just there is a conventional generation, this could be nuclear or oil or coal or natural gas, but these consumers basically transact energy and they are flexible in how much energy they consume, and as a result, they're able to basically come up with an efficient market solution. So that's the idea in here. So obviously there are a significant number of challenges because as you incorporate multiple end users who may be strategic, you really need to make sure that indeed you have an efficient market equilibrium. And these decisions, depending upon the type of market, might be either a regulation market, as a day-ahead market, et cetera. And so that also introduces additional challenges. So the second example I want to give you is one as you go towards a distribution grid. Instead of having, say, for instance, hundreds of units, you now have tens of thousands of units because each one of these things basically is a substation, and this is a feeder that just runs electricity to your street or town or district. And so then it becomes this one of an economies of scale issue. And so the question is, are you really going to be able to not only accommodate the rate at which information is being exchanged, but also make use of the amount of uncertainty that you have and the real-time information as efficiently as possible. So certain things, this is a timescale question in here, but the idea here basically is that local information basically is available to you more quickly and easily and can be integrated, whereas more global ones give you a lot with a lot less granularity, but they do give you global optimization things to watch out for. And so one thing that comes into the picture, and that again intersects with the kinds of decisions at a regulatory level, which is that at a retail level, is it possible then to have a market to facilitate perhaps some sort of a bilateral exchange of information and make decisions so that you can then incentivize distributed generation to basically provide the right kind of support in order to deal with uncertainties that you might have either in the load or in terms of what the central unit is able to supply. So those are the kinds of issues that over here. And the last thing that I want to bring up is natural gas. So one of the, for example, what you see in here is the amount of generation mix. This is from the ISO New England, Boston area where I live. So typically what you want is to balance demand with generation, but the trends obviously is that as you introduce more and more solar wind, and for various reasons coal and nuclear might be phased out, that natural gas might be the right standby. And in fact, in the New England area, natural gas is actually the sole source that is reliable and is reasonably clean. So what that means is that you essentially have a dependence on higher and higher amount of natural gas. And so which means that the access to natural gas from the natural gas power producer has to be managed. But there is a lot of, so this is where the infrastructure interdependence becomes important. And so the misalignment has to be really examined, because if you don't, then you can have these frequency fluctuations. So another interesting thing is that, is it possible to address it by having some sort of a reliability contract? Because as you really increase the renewable penetration to not what the current level is in the United States, around 10, 15% to 20 and 30 and 50 and beyond, as is happening in Spain and in Denmark and Germany, then you really need to make sure that there aren't some anomalies that are of significant concern that can basically come down the pike. Like, for instance, there could be a scenario where the market ISO basically imposes significant amount of penalty because of unmet commitment. So if we did a study where we looked at 2 different plants in Maine, and we said if the wind power and natural gas were to have a reliability contract, then some of these things can be actually compensated. And so the idea is that the wind producer basically has a more aggressive bid, and whatever the wind producer is not able to do, natural gas basically steps in, and by doing that you have improved wind utilization. And so when we looked at the numbers and we did this thought experiment, essentially the wind power producer has more profit because they're able to bid more aggressively, and the natural gas basically realizes a better capacity utilization because they have much lower capacity factor. So there are these opportunities, and so here too, there are a significant number of challenges here, and which are that the kinds of uncertainties and intermittencies as you go towards these high penetration become significant, and the conflict between what might be a local objective and a global outcome are significant. So you really do need to have multiple decision-making authorities that are well coordinated and function at the right timescales. And you really need to worry about the fact that these regulation structures, I mean, the gas infrastructure, for instance, in the United States has been deregulated for a much longer time than the electricity one. And so that in turn has led to its own set of practices, which by and large have not really been an issue. But when you start to make some of these smart energy system decisions, you do need to worry about a different kind of a framework with which you look at these things. So, and when you want to really realize a smart energy system that gives you resilient and reliable power delivery with 100% renewables, which is really the utopia that we want to realize, you do need to have these multiple entities come together and really figure out how you can make this real-time decision-making between disparate agents. And this kind of a thing is what we've been actually exploring in our collaborations with researchers from Japan, and this is a joint partnership between JST and NSF, and so we have a number of exchange visitors going back and forth and to realize this. We have another project with India where the needs are different, and it's not only what was mentioned that I'm glad to hear that the policymakers are interested in looking at privacy issues, but India is a country where 30% of the population does not have electricity. 30% of the power generation is lost due to theft. And so those are significant numbers, and what we're trying to look at is ways in which we can use technology in order to circumvent some of these compelling statistics. Thank you.
Thank you for keeping us honest by showing us some equations, Anu. So next and last but certainly not least, Kishan Beheti will talk about some of NSF's programs in the smart energy space.
Hello, good afternoon. It is very hard to concentrate after lunch, but I hope that the problem with academics is we always talk about this technical lingo. So please excuse us for. So what I'm going to do is I'm going to talk about what are the research challenges the research community funded by NSF is really looking at. And this is a very brief overview. And in my mind, I think the electric power grid is one of the prime example of cyber physical systems. So the idea of the CPS is really bring ideas from different domain and trying to find some common principles and interests where we can really use in different domains. So coming back, which way to go? Which way?
This one, I guess.
Okay, thank you. So if you look at the energy management And again, I'll be talking mostly about the next generation of electric power grid. So the research focus is really basically all aspects of modeling, analysis, design, levels of optimization, and different levels of learning, adaptation, and control of smart, we call it smart grid or electric power grid. And this is again common in many, many complex engineering systems. So if you look at the electric power, it have massive data, and many of the decision has to be made in real time. And many of these subsystems are networked and controlled at multiple and sometimes extreme time scales, from milliseconds to hours. And all this has to work together. They're always dynamically reorganizing, reconfiguring, maybe a man-made disaster or natural disaster. And we have to make sure that with all this, as a systems engineer, you got to provide a dependable operation with high assurance. And then you have to worry about reliability, safety, cyber security, and usability. And all this, the idea of the NSF research to really bring the common principles which comes out of this, which can be used by many, many different domains. So let's look at what are the research trends in the academic community. Again, just to keep things simple, I'm trying to divide into different sub areas. If you look at the network control systems, and again, these are in transportation, power grid, healthcare, all these areas. So one of the things what we're really looking for, that all these systems have continuous models and discrete models, a lot of jumps. And we don't have the mathematical theory to really guarantee some kind of performance. And that's what we are asking basic questions. The whole idea of distributed decisions, everybody, the game theory, people are making their own decisions with the local information. And how do we make sure that all these, don't have any unintended consequences, and also try to get towards the global goal. And one of the major challenges is this distributed optimization algorithm, because as the things get more and more complex, for example, a typical power grid may have 1 million, dynamical equations with 600,000 constraints. And how do you do this in real time is a major challenge. And also, how do you come to a global minimum, not get stuck into local minimum? So a lot of the academic community, we are trying to see how we can, different mathematicians, control engineers, communication engineers, computer scientists come together and solve this problem. And also the scalable, faster, distributed, this whole idea of cyber security, cyber physical security, privacy, and all these issues not only common to power grid, but also go across the all CPS domain. The other area very much booming in academia is the learning and adaptive systems. There is, this is only, we are at the very beginning stage of this. How do you combine the model-based algorithm and the data-driven methods? I don't think we have any clue how to do this. This machine learning has been very successful in image processing, in speech recognition, and some of the really good pattern recognition, chess. But how do you bring this to the engineering systems when you are doing real-time data, real-time decision? And I think, unless we bring these communities together, we really won't have any, the whole idea of deep learning, and how can we, apply with the model-based systems? And are there many different architectures of neural nets? What are the applications? What are their limitations? Where should be used? It's not a one size fits all. So looking at the grid, I think this is one of the best, example for academia to work with, because you name any complex problem and the grid has it. You got all these variables, integration of solar, wind, storage, and also they are time varying, unpredictable, all these things. You want to make sure you monitor correct protection, and also guarantee some resiliency. You want to make sure that you don't get a blackout. Again, the whole area of cyber security, people are trying to attack the grid at different levels. And there are many players in this space. You have the markets, you have consumers trying to optimize themselves. There are wholesale energy markets, and the whole area of consumer behavior. And also the type of loads is changing. You have a lot of digital, different type of loads. The microgrid, what are the economics of microgrid? And the whole area of data centers, they are consuming so much energy. How do you make sure that they will not affect the grid? And also there is a major revolution in power electronics. There is a tremendous things going on in power electronics. You have these solar and wind generators. How do you connect them to the grid? What are the energy efficient power electronic converters? And the whole area of hybrid and electric vehicles, how do they connect with the grid? What is the connection between the transmission and the energy? Storage devices, again, the new power electronics into the electrical machines. So all these, there are a lot of research going on in these areas. So let's, focus on the next generation power grid. I call it a digital grid. And you are seeing that there is an extensive deployment of sensing, communication, and information technology. At the same time, the demand is changing and the consumer expectations are much higher. And also, there is a, resilience is the most important thing because nobody wants to be out of power. That is a tremendous cost. And at the same time, grid is generating massive data at different time scales. And you have to make a real-time decision. So the academic community is really looking at what are the basic foundational research which we can develop, which can be used not only for a given grid, but can be transported across many, many different areas. So let's just look at in the time scale. If you look at the power grid, it has, you have this phasor measurement units. They are collecting data at milliseconds. They are, and there are all over the grid. Then you have these smart meters, millions of smart meters trying to, collect data and trying to connect with the power grid. And then you have this SCADA, which is the, supervisory control and data acquisition systems. They can go, the time scale is from milliseconds to the hours. And you have different aspects of grids. You have a lot of physical models. You have data-driven models. You got to worry about transient machine dynamics. At the same time, at the steady state, millions of, how do you make sure that there is an optimal power flow across the grid? How do you manage the economics of it, markets? And so this is a tremendous opportunity for the data scientists to really look at the data and try to make, decisions, looking at the market bidding, phase detection, state estimation. And I think, this is an interesting problem for the academia. So another very important thing at NSF, we worry about education. And because of the historical reason, what happened was there is a tremendous shortage of energy and power faculty in US universities. In USA, we have about 300 electrical computer engineering departments. And many of them don't have power faculty. And that has been a major challenge. So NSF is working with the Electrical Computer Engineering Department Head Association. And we really have a very good partnership where NSF with the faculty, we are trying to, we started many workshops. I just want to give you an example where we brought about 50 faculty, let's say in one workshop from 50 different academics and trying to see how we can, at least give them some basic, what are the things available. And these are people in control, signal processing, communication, and they have the same background except not in the power. So how does the cyber technology meets with the electric power grid? Because the students really want to. And I just want to give one example, very successful story in USA, and the credit goes to Professor Ned Mohan from University of Minnesota. This professor, they have single-handedly last 10, 15 years, he made his goal to make the electric energy systems education with emphasis on sustainable power. And with the support from NSF, NASA, Office of Naval Research, DOE, and Electric Power Institute, now he has established a consortium of 224 US universities, where every year he does, we have done about 35 workshops so far, and bring, this faculty and some of the people who are really willing to learn the power and give them all the curriculum, also the flipped classroom and all those things. He really taught a lot of people. And I think, you can see it took a person with dedication, vision, and, some kind of a, really mission to really make an impact on the education. But, we are not done yet. We are still way, behind what's going on. So what we have done is, again, this request came to NSF from Japan. Our colleagues in the JST, they approached NSF, and they wanted to see how we can collaborate, international collaboration in distributed energy management. Because energy problem is not only one country, but it is global. Every country has the, similar challenges. The whole electric power grid is restructuring, going through the is all winners and losers, new markets. And so what we did is first visit, we did 4 workshops. First we started with Hawaii, and our colleagues from Japan, they brought about 50 researchers. And then we had people from Germany and USA, and also mainland as well as Hawaii. And then we brought this research together, and again, they had a broad spectrum of areas in power systems, system science, control theory, information technology, communication, and social sciences, because all these communities have to work together. And this workshop, and first one we did in Hawaii, second was done in Washington, D.C., third one, we took our PIs to Germany, and the last year, we met in Japan, in Tokyo. And the goal was to really introduce especially a lot of the career awardees from NSF. And then the idea was to make the networking. And it's not only the networking, but after that, the people followed through it. There was a lot of short-term student exchange, short-term visits, and also joint publications, because they found that there is a, impedance there. So I think, this workshop, the really advantage of this workshop is to bringing people together. But the workshop is only the step 0. It is how we can follow through, and it has to be a value proposition. It has to be on both sides, because the time is the most important thing. And if people think there is a value, they will spend time. And NSF didn't have to put too many resources. If the research community themselves, they wanted to see, they found that what we gave them was a platform, and they used that one. So hopefully this type of activities does have, but there is a lot of follow-up. So just to summarize my talk, in our mind, the electric power system is a critical national infrastructure for modern society, and it is going through a lot of restructuring and transformation, because there are a lot of new players are coming. And also the education. We have to educate the next generation of engineers, computer scientists, and policymakers, because this is critical. And, and also if done in a right way, because everything is a cost of time and, money. But if there is a right way, there is a, definitely opportunity, not only in energy, but any of the CPS ideas. So I just stop there.
Thank you, Kishan. I think that model of how NSF has worked with Japan and Germany and Norway is kind of an interesting sort of top-down, bottom-up combination there. So it's time for some Q&A and discussion. And I thought I'd just sort of, one thing that Kishan said and was brought up in other presentations as well, I thought I'd just start by offering some comments and related to this thought. And then we'll open it up for the rest of you as well. So this notion about IoT and CPS and all the data that's being generated, and we keep talking about the importance of the data. And it's one thing though to think about this data being used for, playing video games or buying the sneakers you're looking for most conveniently or something. But when we start talking about these cyber-physical systems that are safety critical, where autonomous vehicles are driving or energy systems are working, there's an issue in my mind about the limitations of the data we collect and the criticality of systems that we are trying to manage and optimize and control, right? So You may have collect data over the summer in an energy system, and now you are going to develop models from that and apply it in winter. Or you've trained your autonomous vehicle based on data you've collected in some situations, obviously not the entire possible world of situations it's going to encounter, and now it's going to be on the street. So what's the answer here? How can we resolve this issue about the inevitable paucity of data compared to the systems in which these critical systems will be operating? Sebastian.
Yes, it's a very hot topic because, I mean, this community is very much under pressure from machine learning, etc. So people who understand dynamics and models, etc., they get challenged that everything should be much simpler. And I think the answer is somehow twofold. I would say in energy systems, in chemical production, in robots, you would simply be careful. I mean, you would simply not run an electric grid based on some learning method where you don't really understand what the results are and where you cannot check the data before. So you will take a very conservative approach. The, let's say, game changer is autonomous driving, because in autonomous driving, people are putting these systems on the road. And as we all know, it does not always work out. But I mean, that's sort of the area where most of things are going on and where the issue is the most pressing. I don't understand enough of it to say something, but maybe there are people in the room who can comment on it.
Can I add? So when it comes to paucity of data, I would break it down in about 3 or 4 levels. Big data doesn't necessarily mean good data. So the community, the controls community, I think we worry a lot about whether or not the actual data that you have is enough for the machine learning entity to operate. In fact, one of the programs that Kishan was talking about is directed towards that, and I believe there are a number of researchers working towards that. The second thing I would say is big data doesn't necessarily mean that you protect yourself against corrupt data. And so that, when it comes to, say, for instance, what happened with in Ukraine with that cyber attack, and there's been a number of other instances where the adversarial thing would be that somebody, the hacker, sits in there and is stealthy and monitors and deliberately, distorts the data, and that can be really significant. And the last part is big data doesn't really, you have to protect against sensitive data, which was mentioned in the panel earlier today. So that, I think, is going to be one of the biggest challenges for CPS and IoT. And we're beginning to address cybersecurity, which Kishan mentioned again, I think from various perspectives, including in the smart energy space. But that, I think, is a significant challenge, especially as you go towards the consumer and the end user, as to how do you make sure that you use the data for the right purposes for reliability and at the same time protect the privacy.
All right, any questions? Jonathan, yes.
It's slightly following up on what Tariq said. I'm a theorist, so I'm very interested in, when we play games on networks, you look at behavior in a network, and you look at what happens when you allow the network to be reconfigured by the parties in roughly the same time scale. And so one of the things that struck me was we have a kind of thinking approach, which is, let's call it an engineering or managerial one, where you concentrate the responsibility for achieving an optimum, and you then implement it perhaps in a decentralized way. There's another way of thinking, which is more complex adaptive systems, which are that there are these emergent behaviors. They can't necessarily be anticipated, but with enough data, they could be predicted, at least to some degree. And the policy then adapts to what it is you can and can't actually predict. And I was wondering whether there's much thinking, I assume there must be, that in a certain sense, all these electric grids are the easiest example, because electrons follow the shortest path, the operation of the system is fairly rigid. If you think about something like automated financial trading, you get these sort of other phenomena that happen. I mean, it could be flash crashes, it could just be the creation of derivatives. And so to a certain extent, in the longer time scales, for example, when people have feed-in tariffs and install their own generating capacity, that changes the dynamics of the network. It also changes their behavior. But to come back to Tariq's point, the other thing that it changes is the nature and the amounts of data that you have available. Because it seems to me that both the risks and the data about the risks are endogenous to these large complex systems. And until we get a handle on that, if we're still trying to solve the engineering problem, we will continually, I think, perhaps be surprised. So I guess the question was whether within the domain of these industrial IoT systems, the operation of these decentralized control systems and so on, there was an attempt actually to relax the controls a little bit, despite the criticality of these systems, to see what might come out from just kind of messing around or dealing with that emergence.
Well, I think that we are generally averse to messing around with nuclear power plants or even natural gas-fired power plants or autonomous vehicles in that sense. But your remark on electrons following the shortest path, I think in a way suggests a way to look at this whole issue that not that it's a complete answer, but it suggests a direction, and that is that these systems are physical systems and they follow laws of physics. And those laws of physics, in some cases, of course, constrain what flexibility and freedom you might have, but they also tell you when things could go wrong. You have some fundamental knowledge that is over and above and perhaps beyond and more valuable than just the data itself. So, you know, and Kishan mentioned in one of his programs sort of this data-driven and model-driven, and how do you combine those? So I think that's a part of the answer as well.
That was the question I was going to ask. That these physical systems have potential functions that and regularize their behavior. Human systems probably not, and their bifurcations of behavior may be more challenging, but be an opportunity.
Any other comments?
Yeah, you know, I just wanted, you know, this is we are still the beginning stage of this data revolution, because most of the engineers, we always had these, input-output dynamical models, which were simple. Same thing with economics, you know, you have these very simplified models, and there was always a safety of margin. The biggest revolution happened was in the image processing. If you look at the success story of, because that community, they found that this deep learning really brings the error much more down. Same thing happened with the speech recognition and all those things. So this is still an open research. In engineering system, we have to close the loop. And in some of the pattern recognition system, the closing the loop is such a very low level that the consequences are not that bad. So there are some, it's a risk management and trade-off. And I think, the research community is really looking at where the deep learning will be useful and where it is not. And, what are the limits? And, because we really have to be open to this community. If we say, okay, we know everything, then we are done. I think, they have something to offer. And the type of data we never had this much data before. So there are open issues right now.
If I could add, so a complete answer to your question, I think, is a 2-day workshop minimum. But absolutely, I'm in concurrence with what Kishan said. It's a research challenge. In fact, there's a whole field called cyber-physical human systems that is actually being looked at. And we do rely on the laws of physics to basically guide in terms of what is truth and what is corrupted. And we hope, two things I think we count on when we try to connect with humans in the loop or on the loop or for the loop, et cetera. One is that we hope that by having laws of averaging will apply. And so when you put a lot of them together, there's some collective behavior that appears. Second is, of course, strategic performance is always true when you bring a human into the picture. We all lie, but hopefully we all lie slightly differently. And so that when we put us all together, we are able to somehow figure out how things work. But it is very much a work in progress, and I think there's a lot to be learned by. In fact, one of the other initiatives that NSF has, I've been a beneficiary of, is to bring social, behavioral economists together, and I have a project we try to work together so that we can really understand how to figure out this interface.
If I can make a quick remark to this, I think the assumption that technical systems in that respect are simpler than human-controlled systems is not true. In the European power systems, there have been long-term oscillations from north to south, which were very difficult to explain, although this is a purely physical and automatic control system. And on the other hand, if you look at road traffic, then you can think every driver has a different behavior, different preferences, etc., etc. But without looking at the individual driver, you can predict traffic jams very easily, because there are sort of fundamental phenomena that emerge if you average enough. So if you have sufficiently large numbers, then sort of everything can happen.
Both are complex, yes. Yeah.
This was a great panel. They've all been great. But I have an idea. So I've been working I'm Florence Hudson. I'm representing the Northeast Big Data Innovation Hub out of Columbia University today. And one of the things we've been working on with IEEE and the National Science Foundation for the last couple of years is a framework we created out of a workshop at GW University on end-to-end trust and security for the Internet of Things. And we've been publishing about it. I don't know if you've seen it, but there's a framework we created called Tips for IoT. We tried to make it very comprehensive. It stands for trust, identity, privacy, protection, safety, and security. And I'm wondering if maybe we could have a transatlantic collaboration on this, because what we're trying to do is increase the awareness of these issues for the researchers, for the manufacturers, for the citizens, and the regulators, to see if we can actually enable, a safer, more protected environment as everything gets connected. And it relates to all the systems you're talking about. It's connected vehicles, we're looking at it in healthcare, it's the grid, which they've been dealing with this forever. They're kind of DoD-ish, the grid, the way I look at it, Department of Defense-like. So that's just an idea, and I'd be happy to chat more about it. We actually wrote an article, Enabling Trust and Security, Tips for IoT, in the IEEE Computer Society magazine, March-April edition this year. And there's another one coming out on wearables and medical interoperability with IEEE. And since IEEE is so global, that might be a nice partnership. It's just an idea.
Yeah, thank you. I think it would be an idea.
Well, just a quick remark about it. I mean, as the European Commission member, Peter Fratalin, this morning, he mentioned basically, I mean, all of these terms actually are really hot topics in the European Commission. And a lot of initiatives are going towards that way. So I think bridging the gap between Europe and the US, I think it's a really important thing. I mean, it was in the IoT, it was in smart cities, anything that could help us to bridge the gap, because, I mean, it doesn't really make sense that both regions work in a totally different way, because at the end we are talking about the same stuff. So I'll be happy to talk to you about a little bit about it.
Thank you. I actually have a question specifically for your environment. The presentation was really super interesting. And the question is, do you feel there's a difference in acceptability by consumers in the US versus consumers in Europe for the smart approach to energy and the smart meters, etc., that obviously are connected to the smart grids?
I do not have expertise in, I've not interacted that much with the European side of things in terms of demand response. I probably will defer that to other panelists here. I mean, very anecdotally, I know that the concerns when it comes to privacy are quite different, I think, between, and it varies even state to state, I'm sure, within the United States. For instance, there is a whole thinking in terms of controlling the circulation pumps in swimming pools in Florida, which Floridians are very happy to hand over the management of those devices, as I understand, to the utility, whereas the sense of giving away ownership for that kind of thing might be perhaps different in other parts. So very anecdotally, I know that it's an issue. So certainly, I think when it comes to autonomy and privacy, the sensibility is quite different. But
I mean, just to complement that from the European point of view, yes, there are big differences. For example, smart metering is a dead subject in Germany. There is no pressure on the private households to introduce it anymore for two reasons. One is that it is costly, or three reasons. It's costly. People are very concerned about their privacy, which is a bit neurotic, if we are honest. And thirdly, there is not much to be gained, because we don't use so much electric power for air conditioning and for swimming pool pumps. And that's an interesting, I wanted to come to this issue, an interesting interaction between human factors and technical factors, because it is an interesting question. What does it take to bring the consumer to start or to empty more the washing machine at 5 o'clock in the morning because the power was more abundant in the night because you could not switch off your nuclear plant or something like that, okay? So when it also involves human behaviors, and I think the conclusion is that in the household, both the financial gains on the household side and the overall gains for the system are not as big as in industry. So in Germany, the focus on demand-side response is very much on industrial demand-side response, where you have big consumers, which are also more rational than the owners of washing machines.
That's true in the US too. I think the demand response in buildings is become more prominent. Actually, that made me just sort of, reminded me also of the discussion we had this morning, where I think, Glenn, it was you who was talking about sort of this asymmetry in valuing data on the part of consumers on the one hand, and who don't appreciate perhaps what that data is worth, and the companies who are collecting this data. It's not quite the same. It's not really a true analogy, but it's sort of this issue about on the energy side, smart energy side, seems similar to me. Here are consumers who can save some energy by making some actions and perhaps by investing something, but maybe not even no financial investment involved, just making some behavioral change. And it'll save them a few dollars a month or something like that on the bill. On the other hand, at the level of the society, that's a tremendous saving if all or the majority of households were to do it, right? So how do we get around this challenge of recognizing that at the individual level there isn't enough incentive, but at the level of the society, at the level of the national priorities that we have and international priorities we have for climate change, for example, that this is something that needs to happen. And I'm not quite sure what the answer is. Yeah, you can try nudges, and there's some behavioral economics work that's relevant, but I think a lot more needs to be done there. So I see we're just a little bit over time. We started a little bit over time as well, but I'll see if anybody else has anything to offer or if there's any final question, and if not, we can go and have some more coffee if you haven't had enough already.
Well, I can just follow up on what you said. I mean, demand response as a technology certainly has potential. Like, for instance, what PNNL has demonstrated through its Olympic Peninsula project, that there is significant savings to be had, and they had implemented a fairly, carried out a fairly large-scale experiment and demonstrated the savings can be like about 10% or so. But whether or not that carries over to other parts, there it was, they relied on the fact that there is no deregulation in the northwestern part of United States. But whether or not it carries over to other parts of the country or elsewhere, I think is a harder issue to answer.
All right, any final thoughts or questions from anybody? Thank you very much for your participation. Time for more coffee.